Good day, dear participants. Let me introduce my topic, Combined Multi-Temporal Burned Area Mapping based on Landsat 8 and Sentinel-2 satellites data processing, related to possibilities, difficulties, and perspectives of wildfires research with means of remote sensing. During past years, uncontrollable and destructive wildfires are becoming an expected part of annual calendars. Climate change is affecting global wildfires, such as by increasing the fire season and size of areas affected by fire. Droughts, which might be exacerbated by climate change, can also make wildfires more likely. Devastating fires are widely spread on all continents except in only Antarctica. According to Earth observation research, nowadays every region on Earth has its own wildfire seasons. Wildfires become more and more common in particular parts of Earth. Here you can see global maps of relation between active fires and aerosol optical depth provided by Earth Observatory, where you also can find other global maps particularly related to wildfire hazard. Wildfires related not only with dry weather, but also with human activity like slash and burn farming. It is estimated that nearly 300 million traditional farmers use slash and burn practices. It is widely spread in Central Africa, Bolivia, Brazil, Eastern India, Thailand, Cambodia, and other countries. Particularly on this map that demonstrates wildfires detected by satellites during period from middle of December 2019 to middle of January 2020, the highest wildfire activity is related with areas where slash and burn is mostly widespread. Wildfires causes dense haze that negatively affects highly populated urbanized regions and aggravates ecological problems. The most critical problems related to wildfires are loss of vegetation biomass caused by fire, damaging and destroying ecosystems and habitats, loss of tremendous quantity of animals, atmosphere pollution by combustion products, and aggravating of global greenhouse effect, direct atmosphere heating, and violation of Earth's heat budget. I would like to present you some information about possibilities to use of remote sensing data in the field of prompt response to wildfires, describe some satellite systems, and present some techniques of wildfire detection and burned area mapping on the example of wildfires in my native country Ukraine. Also, we will discuss some met challenges and difficulties as well as perspectives of using satellite data in such kind of research. There are three approaches for wildfire research and response: terrestrial, UF-related approach, and satellite data processing. First includes fire and smoke sensor distribution, visual monitoring, firefight, and other terrestrial efforts. UFs help to promptly detect burning areas and evaluate firefight efforts efficiency. Satellite data allow realizing large-scale fire monitoring systems and burned area mapping for further data accumulation and formation of long-term fire hazard maps. Here is represented a red dot chart for different early fire detection systems. Most of the literature shows that terrestrial systems have been extensively studied, achieving high accuracy rates and fast response times, despite the limited coverage areas that they offer. Thus, large networks of ground sensors can be deployed to increase the coverage area. However, in this case, a trade-off between the number of sensors, cost, and the complexity is required. On the other hand, aerial and satellite-based systems provide better coverage. These systems have already shown their great potential, accuracy rates, and response times. Some countries are actively use satellite data for national fire information systems, particularly Australia and Canada. Firewatch uses satellite instruments to detect current fire hotspots on the ground across Australia. providing the most up-to-date information to both fire management agencies and general public. The Canadian Wildland Fire Information Systems monitor fire danger conditions and fire occurrence across Canada. Daily weather conditions are collected from across Canada and used to produce fire weather and fire behavior maps. In addition, satellites are used to detect fires, and reported fire locations are collected from fire management agencies. The most common satellites which provides data for such national fire watch systems are meteorological satellites like NOAA and Imagery 8, and low-resolution scanning systems like MODIS. Remote sensing satellites always provides a compromise between revisit period, field of view, and spatial resolution. Mentioned satellites are very efficient in prompt hotspot detection, but poor in detailed mapping. So today I would like to present you some techniques for detailed mapping of wildfires and burned areas using moderate resolution satellites data provided by Landsat and Sentinel-2 satellites, which don't allow you to promptly receive data, but this data has much higher spatial resolution. Landsat 8 satellites continuous long-term satellite program started in 1972. Landsat 8 launched in 2013 and it has two sensors, only invisible shortwave and near-infrared ranges, and TIRs, internal infrared range. OLI provides data in 20-bit dynamic range with 30 meters spatial resolution, and TIR sensors provides 100 meters in thermal infrared range. A Landsat 8 scene size is 185 kilometers by 8100 kilometers. Satellite revisit period is 16 days. For some territories, due to path overlapping, it is 8 days or less for polar regions. Landsat data is free, and you can receive it using acquisition tool Earth Explorer, provided by United States Geological Survey after registration. Preprocessed burned area products based on Landsat data, available for downloading but only for US territory. Sentinel-2 is an Earth observation mission from the Copernicus program that is the constellation with two twin satellites, Sentinel-2A and Sentinel-2B. Sentinel provides 12-bit data in 13 spectral bands, both raw and processed into the surface reflectance. Data provided in visible, near-infrared, and short-wave infrared ranges. The spectral resolution starts from 10 meters. Revisit period is 5 days. Sentinel satellites data also totally free, as the data received by other Sentinel program satellites and available for download using acquisition tool provided by European Space Agency. Talking about data that represents wildfires, it can be divided on two general types: burning areas or active fires itself, and burned areas emerged after fires. Each kind of data has its own indicators, input data, and processing procedures. Active fire indicators that could be detected using satellite data are next. Dense smoke, which can be detected even using preview images without any computational processing. Spectral signatures, particularly shortwave and long-wave infrared signals, based on spectral features of different kind of areas and surface temperature. Burned area indicators based on spectral signatures, particularly shortwave and long-wave infrared signals, based on spectral features of different kind of areas. The most common features are normalized burn ratio, near-infrared signals that are represents vegetation condition, normalized burn ratio difference, represented as difference between pre-fire and post-fire NBR indices, vegetation cover change detection. Temperature at the major thermal feature of fires can be estimated using short-wave and long-wave infrared satellite data. Looking at the Wien's displacement law, which shows that radiance peak from objects emitting at temperatures nearly 500 to 700 kelvins is around 2 and 6 micrometers, which is partly covered by Landsat and Sentinel SWIR bands. Data from thermal infrared data in range 8-14 micrometers on satellite orbiting Earth can help by detecting fire hotspots, parts of the land surface that are noticeably warmer than the surrounding area, and its temperature can be estimated using Planck's law. Talking about burned areas, the normalized burn ratio is utilized for the purpose of its mapping. NBR is an index designed to highlight burned areas in large fire zones. Healthy vegetation shows its very high reflectance in near band and low reflectance in SWIR portion of spectrum, the opposite of what is seen in areas devastated by fire. Burned areas demonstrate low reflectance in the near band and high reflectance in SWIR band. Low NBR indices can be related with absence of vegetation for particular areas, and for this reason NBR itself doesn't represent burned areas. For this purpose, we need to evaluate difference between pre-fire and post-fire NBR to detect and delineate the devastated areas. And now let's talk about study area for the practical part of our research. For active fire detecting and burned area mapping, several Landsat 8 and Sentinel-2 satellite images of northern Ukraine received in March and April 2020 during massive wildfires occurred because of very dry winter. In fact, wildfires are typical for these areas because of frequent peat fires and forest fires. Considering hotspots and wildfires itself, Landsat thermal infrared data obtained by TIR sensor was processed. The main factor for imagery selection was the smoke trail observed from preview images. Surface temperature was estimated as well as temperature threshold between burning and non-burning areas. The threshold binary mask for burning areas was formed. Threshold approach allows only to detect actively burning areas, but not burned areas itself, due to high temperature difference. In this case, we may manually delineate burning areas considering active fires. It would be useful for further burned areas mapping, but we should consider that for the moment of sensing, fire was still spreading, and real burning areas often rather larger. The same approach is valid for short-wave infrared data, which is applicable for detecting and mapping active fires even through dense smoke. This data is provided by Landsat and Sentinel-2 satellites. This range is better for hotspot detection because of very high temperature contrast, and we can find many small hotspots. Here is represented how normalized burn ratio difference approach works. After deriving pre-fire and post-fire normalized burn ratio images, the difference between indices has been estimated. For pre-fire data, we used image from 2018, because in 2019 this area was also heavily damaged by wildfires. For difference image, we apply difference ranges levels. The highest difference range recalculates into burned area mask, which could be transformed into vector data. Multispectral imagery classification is useful approach in case when we need to estimate burned areas in different kind of surface types. Each class can be transformed into class mask and applied for burned area image. In case of burned area mapping, using satellite data obtained during vegetation season, near-infrared data itself could be appropriate data without using normalized burn ratio index due to its representation of vegetation condition and clear delineation of burned areas. To generalize efforts for wildfires and burned areas mapping, let me introduce you a decision trees which consistently represents that we need to define for both types of research. Active fires and burned areas mapping allow not only evaluate damaged areas and its recovery, but also data accumulation for formation of long-term wildfire risk maps. Described approach meets many difficulties related to large variety of factors. Firstly, as it was mentioned earlier, for today it is impossible to promptly derive highly detailed satellite data because mutual extinction of these features of images. Secondary, dense cloud cover, haze and smoke hinders deriving correct and clear satellite data. In some areas, cloud cover is almost permanent and there is no possibility to get optical data. Also, it is rather difficult to build profile data in particular territory often suffers from wildfires. We just have no possibility to perform it on burned areas. And now let's talk about some positives related to the discussed topic. First of all, in nearest years, satellites constellation that provides free access data would be expanded. Landsat 9 and two more Sentinel-2 satellites are planned to be launched during period 2021-2023, so availability of relevant and cloud-free data would be highly increased. Shortwave infrared data proved to be a very efficient instrument for searching hotspots through the dense smoke, and this data should be applied for firefight efficiency evaluation. It is important because thermal sensors are not so popular among satellites designers, unlike shortwave infrared data sensors. Also, it is possible to use radar data for burnt area mapping using multi-polarization SAR data. You can visit the link for details. I also would like to share with you the links to special issues of Remote Sensing Journal, which became the basis for this research and different other special thematic issues that might be quite useful for you. Thank you for your attention.